And here is another example of three different amplitudes, and you can see, once again, it's easier to see these in the transverse waves, but you can see the low energy level here, a little bit higher energy level here, and a much greater energy level here. The crest is low, the trough is not that deep. Crest is a little higher, trough is a little deeper, then the crest is very high, trough is much deeper, and you can see the full displacement here is much larger in this big one, this high energy, high amplitude wave, than in these two smaller ones. Here, once again, just another example of these different things we are talking about. The wavelength, one point to one point on the transverse wave. Here, from rarefaction to rarefaction here on the compression or longitudinal wave. This one clearly does not have a high amplitude, as this is not a very tight compression, and this is a kind of cluttered rarefaction, so not a very high energy or high amplitude wave. And we're looking at the amplitude here on the transverse wave, and once again that full displacement. So this is showing us kind of the relationship between wavelength and another concept we're going to talk about called frequency. The wavelength here is much shorter than the wavelength here, which is much longer. Short wavelength, long wavelength. And if you count the number of waves that actually pass by, this shorter wavelength wave obviously has a much greater frequency of waves. So the higher the frequency, obviously the shorter the wavelength. This is another inverse relationship. One goes up, frequency goes up. One goes down, wavelength must be shorter, goes down. Here you have a longer wavelength, and obviously you can see there are much fewer waves in this same 1 second time period. And so here's that concept of frequency. It's how many waves pass a certain point, or how many waves happen, essentially, in a second. So how many waves actually happen in a second? We measure this in hertz. As you can see from the picture here, this yellow box represents 1 second. Here we have a frequency of 4 hertz, 4 waves per second. So hertz is waves per second, 4 waves per second. And you can see this measurement of the wavelength right here, not very big. Here we have the same second of time, and we have only 2 wavelengths. We have 2 hertz, and this wavelength a little larger obviously than this. And then here in that same second, only 1 hertz, and then a much longer wavelength. So frequency and wavelength obviously related. This is a large wavelength, right, and a much smaller frequency. Medium wavelength, larger frequency. Low wavelength, much larger frequency. Wavelength and frequency, inverse relationship. Once again, these have nothing to do with the amplitude, which is the power. Amplitude is the power. Frequency and wavelength, how many waves per second and how long those waves are. Once again, can't stress this enough. Smaller wavelengths result in higher frequencies. Because the waves are so much smaller, there can be so many more of them per second. And the larger wavelengths, obviously, result in a shorter frequency. The longer the wave, not as many of them can pass a point in that second. So, a wavelength with a small wavelength, a wave with a small wavelength, higher frequency, more hertz. Larger wavelength, longer waves, shorter frequency, less hertz. And frequency is measured in hertz. Here we go again. Short wavelength, right? You can see it right here. It's a short wavelength, and look at how many waves we can get, right? High frequency, short wavelength. Low frequency, there's only 1, 2, 3, 4, 5 waves here, right? But look how much longer that wavelength is. we see different colors in the electromagnetic spectrum from the electromagnetic waves, and we hear different pitches from sound because of the differences in wavelength and frequency of light energy right here, light waves, which are a kind of electromagnetic wave, and sound waves, which are a kind of compression or longitudinal waves. Electromagnetic waves are transverse waves, as you can see here, and sound waves are compression waves. So the differences in color that we see and the differences in pitch of the sound that we hear are variances or differences in wavelengths and frequencies. We can also talk about the wave period, how much time it takes for one full wave to actually happen. As you can see here, this person is holding that rope. We're going to create a transverse wave. And how long does it take for that full transverse wave to happen? That is called the wave period. Here it is 1 second, right? How much time does it take for one full wave to happen? That is the wave period. We can also talk about the wave speed. How fast does a wave travel through a medium? Right? Mechanical waves, that is waves that travel through mediums, that must have mediums to work, they travel much faster in a medium that atoms are densely packed together. So clearly a mechanical wave would pass much quicker through a solid than it would through a liquid or a gas. The tighter the material is packed together, the faster a mechanical wave travels. We're talking about compression and longitudinal waves, sound waves, as are mechanical waves, this unit. Those travel faster through more dense materials. Whereas for an electromagnetic wave, that is the exact opposite. If it doesn't need a medium, then the medium is essentially getting in its way. So if there's something getting in its way, the more densely packed those particles are, the more it's going to get in the way of that electromagnetic wave. So electromagnetic waves, they travel much slower in a densely packed medium, which is why in the basement of our school you do not get good cell signal on your cell phone because of all the walls and dirt in the way of the basement, not allowing those electromagnetic waves to travel very easily. So your speed of your wave is your wavelength times the frequency. Very simple. And the wavelength is your speed divided by frequency. See, wavelength and frequency very much so related. And the frequency of your wave, speed divided by wavelength. All these are related to each other. Very related. This guy wants to hear if there's something coming. He can hear the car coming through the ground easier than through the air because, once again, that sound wave, that mechanical wave, is going to travel much faster through the dense ground than it will through the less dense air. So he can hear if something's coming before this way. And so here's the waves, the different kinds of waves that are labeled. Peaks, we call those crests, same thing. Okay, so you need to have these labeled waves in your notes so that you know exactly what is what. Wavelength here, distance from compression to compression. Right, these are the rarefactions, these spread out parts. Wavelength here from crest to crest. Right, this is the complete wave cycle. These are the troughs. This is your measure of amplitude. These are all the things we've talked about. These need to be labeled in your notes. And that is all.